Today I want to talk a bit about what we have found out recently concerning the characterization of ISS via superposition theorems, I have to say. So there will be no Lyapunov functions today. So if you were hoping for Lyapunov functions, sorry. All of this is joint work with Lucas Brivardi, Antoine Chaillet, and Andriy Mironchenko, who's one of the organizers of this fantastic seminar series. And luckily, there's a funding agency that funds collaboration between French and Bavarian researchers, and they were helping us a bit. Okay. Aha. Now what? Okay. So contents, well, a brief introduction about concerning the systems we want to talk about. Then I want to recall some results that you may know and try to place time delay systems in the context. So there are basically two classes. We know the ODE theory, but that is not enough to cover time delay systems. We know general results on infinite dimensional systems. That requires too much. And so basically the question is, time delay systems are a nice class, maybe the nicest class of infinite dimensional systems. And so can we say something more using the particular structure that we have there? It turns out that boundedness of reachability sets will play a crucial role in all of this, and I will try to explain that. And in particular, in light of some recent counterexamples that have been obtained by Mancia, Aguiar, and Haimovich, and some counterexamples that we could build using the technique that these two have developed, right? So we're very grateful to them. And then we can come to ISS characterizations and see what we get from there. Right, so the system class that we look at are systems of that type. X dot is f of x sub t u of t. X of sub t as standard in time delay literature. So we're looking at, well, that's maybe not standard, but that's what we do. We're looking at a fixed maximal time delay. So the delay is bounded. And the state space is the space of continuous functions on the interval minus theta to 0. Yeah, and x sub t is a function in there. And then the trace of the solution, if you want, in Rn is x of t, and the relation between x of t and x sub t is that x t of s. Yeah, this is a function at time s, and s is an element in minus theta 0 is x of t plus s. And we need some conventions so that we don't have technical problems along the way, and so we will assume continuity jointly in both variables. We have our fixed point at 0 because we like to have it there. F is Lipschitz continuous in the state, so in xt on bounded subsets of the state space, so the space of continuous functions, and Rm, and the Lipschitz constant is uniform in U. Yeah, this is quite a bit that we require, but we need most of these things somewhere along the way. Okay, so that's our system class. That's the standard delay system. So existence of solutions is not a problem. The inputs are measurable, essentially bounded functions. And okay, so in this ISS theory, we are all probably fairly used to it, but still let me recall in case someone is not used to it. So class K functions, the symbol calligraphic K, are those functions from the reals to the reals that are continuous, strictly increasing, and 0 at 0. And if this function is unbounded, or if we look at the subclass of this where the function is even unbounded, we call that K infinity. Class L functions are the functions which are continuous and strictly decreasing to 0, as t tends to infinity, and KL are functions in two variables that are continuous. And if I fix the second argument, I end up with a class K function. And if I fix the first argument, I end up with an L function, right? So this is why KL, right? So here in that variable, it's K, and in that variable, it's L. Okay, so that's standard notation that I will use, which is very useful in expressing certain decay properties of solutions of systems. And so here, as introduced by Sontag, quite some time ago, almost 25, no, more than 20, in 1989, a lot longer than 25 years ago. Such a system, the original definition was, of course, for all systems of ordinary differential equations, control systems there, but I mean, the idea is exactly the same, right? So the system is called input to state stable. Yeah, so the word says from input to state, there should be a stability property. And the condition is there's a beta in KL, which is responsible for the effect of the initial condition, and a gamma in K infinity, which is responsible for what U does, so that no matter which initial condition, no matter which input we pick, for all times we have an estimate of this type. So the norm at time t, yeah, so this is the norm then in C, so the infinity norm, is less than beta norm of the initial condition, comma t, and remember this decays in t as t tends to infinity. So this means this term goes away as t tends to infinity, plus gamma from u, and gamma is a k infinity function. So the bound will be less and less informative as the norm of u grows, because this number becomes larger, but still it does so in a continuous way. In particular, if u is small, then this will also be small. So x of t will eventually be small because this tends to 0. Okay, so this is combination of what's the effect of the initial condition, what's the effect of the input, has turned out to be very useful, as most of you probably know. And so it's interesting to be able to tell, okay, what can I say about a system? How can I determine whether it is ISS or not? And there's one big branch of this, which is, of course, find the right Lyapunov function with the right properties that will tell you that the system is ISS. But especially in terms of proofs, it's sometimes useful to have other characterizations. And just as a reminder, so that was noted very early, that it's useful to have other characterizations. So Sontag and Wang for ODE systems in 1996 proved the following. So we have here x dot equals f of x t u of t. Yeah? So x, the state is now in Rn, so no delay here. We have the equivalence input to state stability, uniform local stability, and the limit property holds, or uniform local stability and there's an asymptotic gain. Yeah, so this dynamic property expressed in terms of other dynamic properties. And then, okay, so I have to explain that a bit. What does this actually tell you? So 3 new words have popped up: uniform local stability, limit property, asymptotic gain. So if you look in that paper of 96, you will find the following. So the system is uniformly locally stable if instability, so there's a delta and k functions alpha 1, alpha 2, so that if x and u are small, so both the initial condition and the input are bounded, well, depending on the system, by some delta positive. But if you have that, so if you start close enough to 0 and if the input is small enough, then the trajectory, so the supremum over t positive of the trajectory, so the entire trajectory, does not deviate too much from 0, yeah, because the trajectory is bounded by a continuous function of the norm of the input and a continuous function of the size, initial condition, size of the input, and remember alpha in K means alpha of 0 is 0, right? So that gives you a continuous deviation in the size of x0 and u. So that's stability. If you're familiar with ordinary stability, that looks very reasonable to assume something like this. And then the limit and the asymptotic gain property are more about behavior as time becomes large. Yeah, so the limit property says there's a k infinity function so that for all x0 and u, the infimum of the solution is bounded by gamma of the norm of u. Right? So that doesn't mean that the solution has to be small always or after a certain time, but it has to be small sometime. Yeah, so if no matter which input, which initial condition I pick, if the input is bounded by a certain thing, then the corresponding trajectory has at least to dip down at some time. Then it can grow again, right? This doesn't say too much about that, but that's the limit property. And asymptotic gain says more. Namely, it says that the limit superior, as t tends to infinity, of the norm of the solution should again be bounded in size by a rescaling of the norm of the input. Yeah, so this basically says after some time, it will always be less than gamma of u plus epsilon. Okay, so that's very nice. But if we study time delay systems, it's a guidance, right? So we at least need to require that, because if you want, ODE systems are a limiting case of time delay systems, but time delay system can exhibit more behavior than ODE systems. So you can think, okay, let's look at it from the other way. The state space is infinite dimensional. So let's look at infinite dimensional systems. And if you look at abstract infinite dimensional systems, there's also a characterization of ISS available, right? I'm not redefining that class. Takes a time. At that point, it's probably not so interesting to see what that class looks like. Just let me say that the class encompasses time delay system, of course, but also a lot of other partial differential equations and other things can be put in that form. And there we have another characterization of ISS. The formulation, the definition of ISS is, of course, exactly the same, works nicely as long as the state space that you live in is a Banach space or a norm space, and you also have a reasonable norm on the input functions, which we assume. Yeah, then the definition of ISS reads exactly the same, so I don't have to show that again. And now we have also equivalences to ISS, but then now you see, before with Sontag and Wang, we had the limit property. Now suddenly it has to become the uniform limit property. And that's not enough. We also need something completely new, bounded reachability sets. Or you need uniform asymptotic gain and bounded reachability sets, right? So you see the requirements to conclude that something is ISS, the requirements become a lot stronger. That in a way makes sense because ISS in itself is a uniform property, right? It gives bounds for the norm of the solution based just on the norm of the initial condition and the norm of the input, right? So that in itself is a uniform requirement. So it makes sense that uniformity plays a role in characterizing this, but then this bounded reachability sets also become interesting. And in the general class, all of these properties are really required. Yeah, you can build counterexamples that something fails if you relax one of these, but these counterexamples are all not time delay systems, but some general nonsense systems. And so I have to explain, what does the uniformity mean now? So we remember this was the limit property. there exists a gamma such that the infimum of a solution is bounded by gamma of u, and you see why this is not uniform, right? Because the time at which this happens could depend on x0 in a wild way, and there's absolutely no uniformity in x0 required just from this requirement. So, sorry, wrong direction. So the uniform limit property, what's uniform now? So we want for all epsilon and r, there exists a time which just depends on r and epsilon. And so that for all initial conditions bounded by r, for all inputs bounded in norm by r, we have that the infimum of t in that interval from 0 to t of the norm is bounded by gamma of u plus epsilon, right? So what's the uniformity here? The uniformity is that this bound has to hold basically for all x0 and u in these balls, uniformly in these balls. And the tau is only allowed to depend on the size of the ball and the epsilon bound, upper bound that you, relaxation that you have here, on nothing else. Yeah, in that way it is uniform. And we can play a similar thing with the asymptotic gain. Again, this limit superior as you have it here now, when this happens, can very well define on x0. So there's no uniformity here guaranteed at all. And to have a uniform formulation, well, the same thing happens. We want a time which just depends on the size of the balls, on the relaxation parameter epsilon, such that uniformly for all x0 and u in the respective balls, and all times which are bigger than this tau, which doesn't depend on x0 and u, but just on the size of balls and the epsilon, we have this bound, right? So this is how you go from a normal property to a uniform property. And yeah, but that doesn't explain the role of these bounded reachability sets. And the bounded reachability sets are really interesting for the time delay systems. So I will have to spend some more time on them. Yeah, so what does BRS, as we call it among friends, or bounded reachability sets mean? Well, it means that, again, there's a uniformity here. So I take, again, balls of radius r and a fixed time. And then I look at the supremum of the norm of the solution over all solutions which start somewhere in the ball of radius r, where I apply an input which is bounded by r, and where the time over which I let the system evolve is bounded by this tau here. Yeah, so I get a lot of solutions. So I start in a ball, I have a ball, bounded ball of controls that I can apply, and I have a bounded interval. But I want that this number should be finite, no matter which ball, no matter which tau I pick. This should always be a finite number, right? So infinite time from a bounded ball, I cannot become infinitely large. Interestingly, this property for ODE systems is automatic. Well, ODE systems can explode, of course, then you don't have that property. But that's basically the only thing that can happen. If the system is forward complete, so all solutions exist on 0 infinity, then and the system is sufficiently nice, but not really very weak requirements on F. Then for ODE systems, this property is automatic, and this property is not at all automatic in the infinite dimensional case. I should also note that maybe you're not familiar with this terminology, bounded reachability sets. We like it because we think it's intuitive, because this is basically says we have a bound on the reachable set, but in the literature you will also frequently read the term robust forward completeness, which is exactly the same thing. Well, sometimes there are systems with extra disturbances added here, which can also be robustly forward complete. Then it's different, but for systems of that type, the two words mean the same. Good. So this is what we want to understand. And yeah, for some time, it was a bit unclear whether time delay systems are nice enough so that also what is true for ODE systems also holds for time delay systems. So whether it's true that forward completeness of time delay system implies that we have this property that all reachability sets from bounded sets are bounded. And fantastically, last year, Mancia, Aguiar, and Haimovich found out, no, they have constructed an example which has many, many nice properties, right? So they construct a system which is forward complete. It's even globally asymptotically stable in zero. A system without inputs, I should say. It's locally exponentially stable in zero. It's uniformly attractive in zero. Yeah, but still all of this, right? So basically the entire system wants to go back to zero. But even so, reachability sets need not be bounded. Yeah, and so in particular, the system cannot be uniformly globally asymptotically stable because the uniformity in the global asymptotically stable stability immediately gives you bounded reachable sets, right? So, okay, so, and this example I need to discuss a bit because we want to build on that to find even more things which break for time delay systems. And so what are the building blocks of their example, right? So they had a very clever three-step construction. So they start with a linear switch system with solutions that decay to zero if the switching signal is continuous, and for measurable switching functions, you cannot guarantee that. Yeah, so that such systems exist is, I would say, it has been known in the switch systems literature for a long time. But now the question is, what do you do with that, right? And then already in 2005, Mancia, Aguiar, and Sontag and Wang took such a system and from it constructed a nonlinear switch system, which is not forward complete. So there are solutions which explode. But as soon as you restrict yourself to continuous switching signals, then all solutions exist on zero infinity. Yeah, so that's even more surprising maybe. Yeah, so if you allow yourself to wiggle around in an L infinity sense, solutions can explode, but as long as you change continuously, I mean, continuous can still mean you switch very quickly, but in a continuous fashion, then solutions exist. And last year then, Mancia, Aguiar, and Haimovich saw how you can use these tools to build a delay system with an extra variable, which basically acts as the switching signal, and the system is forward complete, globally asymptotically stable, uniformly globally attractive, but doesn't have bounded reachability sets. And to be a bit more, give you a bit more detail, so this is the linear switch system. If you look at it a bit, okay, the two matrices have trace negative, determinant positive. So we are switching between two stable systems, Hurwitz, I mean, linear exponentially stable. And it's well known that switching between them can still be unstable. And the nonlinear modification that they looked at was, okay, so phi of u is basically a function which cuts off the switching signal at between 0 and 1. It's a standard cutoff function, so I didn't want to write that down. So nothing much happens here. So phi will just put u to 0 if it's negative and u to 1 if it's positive, and u is just a real parameter. And this term, of course, is what hurts you, because this nonlinearity, as you all are familiar with, makes system explode because of this norm x squared there. right? And this system is indeed, as long as the U, the switching signal here, is a continuous function, this cannot explode by continuity because, and the argument is, each of these matrices is, and actually the entire interval of these matrices consists of stable matrices. So for every fixed value of U, you have here a stable matrix. So the system actually wants to go down to 0. Locally always. It's just that the switching makes it still explode, right? And explodes faster and faster as X becomes large. So if you switch discontinuously, solutions really can cease to exist. And the delay system is very clever, a very neat idea to say, well, here the U in this system, the U is still the switching signal. But the switching signal could just be another state of the delay system. And if you start with a delay of 1, for instance, I mean, 1 doesn't really matter, some number, and your state space is the continuous function on -1, 0, then basically on the first interval where you prescribe the initial condition of Z1, you can put continuously but arbitrarily weird switching signal that make this system here behave in a bad way. And so on the interval 0, 1, this is actually behaves like a continuous switching signal. And then afterwards, because of this will decay exponentially to 0. Yeah. There's actually no delay in the Z1 variable at all. And okay, so this system has the property that if you switch fast enough, solutions explode. So that means, and you can approximate the switching signal with continuous switching signals. And so solutions become arbitrarily large, right? And so you can prescribe an initial condition for Z1 on the interval -1, 0, but make this system here become arbitrarily large over the interval 0, 1. And afterwards, everything nicely goes back to 0, because afterwards Z1 converges to 0. This will converge to A0, which is a stable matrix. This makes the system extremely fast if X is large. So you really decay extremely quickly back to 0. And this is what gives you the uniform asymptotic gain. The uniform global attractivity of the system. Even those trajectories grow on the interval 0, 1 as large as you want if Z1 starts in the right way. And yeah, so we played a bit with this example and found out a few more things, right? So we can build now a 4-dimensional delay system without inputs, which has the limit property, but not the uniform limit property, right? So that also answers the question whether for time delay systems the limit property implies uniform limit property. No. And then we can also build a system which is globally asymptotically stable, but not uniformly globally attractive, right? So remember this system, these two questions were not answered by the example of Mancia and Heimovich, because I mean, they tried in a way to create an example which is extreme in the sense that it has all the nice properties, but not bounded reachability sets, but then it was uniformly globally attractive, right? And so question whether it's possible to not do that was a bit open. And so this is the example they had. And so we will modify that in a small way. So this is the nonlinearity. And the nonlinearity makes our solutions grow very quickly on the interval 0, 1. But then remember, it also makes the solutions decay extremely rapidly beyond 1, right? Because if x is large, then will be more or less a stable system. And the 1 plus x squared means finite existence times backward in time. So you go back to 0 in finite time, which gives you the... And so we wanted to get rid of that. And then we thought, yeah, but we've learned now how to do this, right? So you can use delays to mimic what a switching signal does. So we build in one further switch, namely a switch which turns off this dynamics, which is extremely fast, back to 0 beyond 1, right? And so we go to R4 because we need another switching signal, Z2. We need more time. Oh, yeah, so this -1 should change to -2. We need more time, so the new switching signal now has a delay of 2. And on the interval 0, 1, we will just let this system do its thing as we have all the nice properties from the counterexample that was already there. And then basically this term is there to switch off this signal and switch back to a nice, exponentially stable, but not very fast system, right? So the solutions go as far away from 0 as you want on the interval 0, 1, and then they decay back to 0, but they decay this only, I have to say, only at an exponential rate. And so that means you can take arbitrarily long to actually come close to 0 if you start in a bounded set. So you have the limit property because you still have this decay, but not uniform. And you have global asymptotic stability because in the end, everything will decay exponentially with this dynamics here, but not uniform. Right, and so this is the way the switching signals work. So basically the Z1 switching signal, you can think of like this. So to make the nonlinear system explode, what you have to do is to switch faster and faster between the two matrices and basically have a zeno point at one point. And this is where the point where the solution explodes. And if you want to approximate that by a continuous signal, so that what I described is this gray switching signal here, which just really jumps back and forth between 0 and 1. And now we need a continuous approximation, and that's this black line, right? And that we can do sometime, but in the zeno point, of course, that fails. You cannot recreate the zeno point with a continuous function if you want to continue continuously. And so you just do this up to a certain time. So you give yourself some delay tau m where you stop doing that. But in that time, you can grow as large as you want, depending on how small you choose this cutoff point where you say, okay, now I quit following this zeno behavior of the bad switching signal, of the bad discontinuous switching signal. And the second initial condition for the other system is really very, very trivial. Yeah, you start with the system 1, and then in a finite small time, you switch to the other system. That's all that's required. So the work is really in the initial condition for the first system that makes this work. And so, right, the moral for delays is for delay systems, bounded reachability sets. That is a property that if your state space are the space of continuous function is not something that you get for free from something else that you would like to require anyway. Yeah, I mean, of course, you can imply require global asymptotic stability, but then you're requiring a lot more than just bounded reachability sets. So if you just want that, then yeah, then you have to require that, unless you use Lyapunov functions, which would give you something. But there's an interesting thing to note there. That's really a question of the state space, because we have here this nice theorem by Karafillis, Pepe, Chaillet, and Wang from 2022. And they said, okay, the state space isn't really fixed. We can look at other spaces, right? We can look at W1P minus theta 0, where P is bigger than 1, could be infinity. Yeah, so you want absolutely continuous function where the derivative is integrable in a nice sense. And if you take state spaces like this, then forward completeness implies bounded reachable sets. Yeah, so you could argue, yeah, what this requirement that the state spaces are the continuous functions, that's maybe the mistake. Or I don't know if there's a mistake here, right? And if you look at the example, it's clear why that is, because if you look at our switching signal, if you want to approximate the light gray switching signal here by a continuous function, and here you start with switching faster and faster, if you want to approximate that absolutely continuously, then of course the integral of the derivative will become large, right? So you're leaving bounded balls in the Sobolev space in that approximation. And so the question of boundedness of reachability set is not affected, right? So this is really an example where you do not do it hurts you if you look at norms of the derivative in some sense. Right. Good. So for time delay systems, we don't get bounded reachability sets for free. Yeah, we have to require them. But then, luckily, if you do start saying, okay, we simply have to assume that because examples show that you do not get it for free, then with the assumption you get that the limit property actually implies the uniform limit property. Yeah, something that is completely wrong for abstract infinite dimensional systems. And yeah, I don't have much time for the proof, so I'm not even trying to attempt that. Just as a comment, let me say, in the finite dimensional case, the proof, of course, relies very much on compactness. And that is, in a way, still true here. It's just that compactness, of course, comes in a different guise. Compactness in C, in the space of continuous functions, is characterized by the Arzelà-Ascoli theorem. And you can use that characterization to actually get the required steps. And all of this relies on BRS, because once you know that you cannot leave, if you start in a bounded ball with certain bounds in the norm on a finite interval, that you cannot leave a certain bigger bounded ball, then the right-hand side of the differential equation will be bounded on that bigger ball. So you have a uniform bound on the derivative of that function, right? And uniform bound on the derivative of the function gives you equicontinuity. And then you're in business for applying Arzelà-Ascoli. Good. And with this, then we can get a characterization of ISS for delay systems. We have an equivalence for ISS, and bounded reachability sets we have to require because we do not get it from free from anywhere else. Uniform local stability and the limit property, and then the same you can do with asymptotic gain. Yeah, and so the moral is, in the general infinite dimensional context, we always required uniformity. We required uniformity of the limit property, we required uniformity of the asymptotic gain, and that you do not get for free in the general infinite dimensional case. but here you do get it for free. Yeah, and so if we go back to the ODE system, so what was happened is that we require basically in that old characterization that we have, the thing that for ODE systems you get for free, bounded reachability sets, we have to require on top. And then we have that. Okay, that's basically what I wanted to say. So conclusions, to wrap up again, what was this about? So we have this example of Mancia, Aguiar, and Haimovich, which says forward completeness does not imply bounded reachability sets. Actually, even forward completeness and a lot of other nice properties that you could hope help in some way do not help. You still do not get bounded reachability sets. Then the limit property does not imply the uniform limit property. Global asymptotic stability does not imply uniform global attractivity. And the key role in all of that was something that you simply do not get for free as boundedness of reachability sets. And this property is basically largely, as far as I see it now, independent of the other dynamic properties that we like to think about. And the superposition theorems for time delay systems that we have now are tied in that sense. We take the ODE conditions that we need anyway for ODEs, and we just assume BRS on top. Okay, thanks very much.